Alright, so here is a video on a velocity versus time graph. This is the velocity time graph of the motion, for the motion of a car on a straight track is shown below. It's just assume that the car starts at the origin x is equal to 0. So we know here our initial position is equal to 0, which makes things easy. If you need to, pause the video and read the parts or write it down, A, B, C, D, E, F, and G. For the sake of time, I will go ahead and show you how to attack these different parts. Alright, let's do it. Let's go ahead and crack out part A and B on this particular slide. Part A asks us to find the average acceleration during the first 3 seconds. Right away, we can use common sense here. This is a velocity versus time graph, so the first thing you should identify or be able to extract is that the slope of a velocity versus time graph is your acceleration. But for the first 3 seconds, as indicated on the graph here, here's 0 second, here's 2, here's 3, here's 4. If I go all the way up and meets the graph, the slope for the first 3 seconds here is 0 because it is a straight horizontal line. Why? Because at times equal to 0, the initial velocity is a positive 8 meters per second. At times equal to 1, the velocity is also positive 8 meters per second. And so on at 2 seconds, it stays the same. And then at 3 seconds, it's also a positive 8 meters per second. Therefore, the car is moving at a constant rate of 8 meters per second, which suggests that it is not speeding up nor is it slowing down. Therefore, we say that the acceleration is 0 because the velocity is not changing. Okay, so by definition, you only accelerate if your velocity changes. But if your velocity doesn't change, your acceleration is 0. But we can do it mathematically here to prove to you that it is 0. The average acceleration here is just change in velocity over change in time. Therefore, we can break up delta v into vf minus vi over change in time. And then final velocity at 3 seconds. It's important to keep the time interval here as we practice. It's just the first 3 seconds, suggesting that it starts at 0 second and it ends at 3. If you follow the graph at 3 seconds, you go up, the velocity is 8. And then at 0 second, you go up, the velocity is also 8. So therefore, my final velocity at 3 seconds is 8. My initial velocity at 0 seconds also 8. 8 minus 8 is 0. 0 divided by 3 seconds is just 0. So therefore, the answer for this one is 0, which is consistent with what we concluded earlier. The slope of a velocity time graph is your acceleration, but there is no slope here. The slope is 0, as I indicated here on my graph. Therefore, we can safely say that the acceleration is equal to 0. All right, let's do part B. Part B asks us to find the average velocity during the first 3 seconds. Well, to find average velocity, the average velocity function here is displacement over time. So we can find the displacement really quick. Displacement is simply VIT plus 1/2 AT squared. Now we just plug in values. We know that the acceleration for the first 3 seconds is 0. We just found that in part A. Or we can just look at the graph itself. This is a velocity time graph. The slope here is 0, which indicates that acceleration is 0. So the 1/2 AT squared term cancels out because 1/2 times 0 times t squared is just 0. So therefore, it's pretty basic. VI is 8. How do we know VI is 8? Because on the graph, at times equal to 0, you go all the way up to where the graph is, and this would be a value of 8 because each of these interval is 2. So it would be 2, 4, 6, 8, and 10. So every line is 2. So if you go up to the graph, that's 8. Well, how much time has gone by? It says the first 3 seconds. So therefore, I would just plug in my time as 3 seconds. So 8 times 3 is just 24 meters. Okay. So therefore, I know my displacement. The other way to find displacement is simply by looking at the area underneath a velocity versus time graph. The only thing you have to be super careful about is to shade the right area. So here, if you just shade in the first 3 seconds, so watch my cursor, it'll be from 0 to 1, 1 to 2, 2 to 3, and I go up to where the graph is. If I were to shade this area, the base would be 3 because it'll be 1, 2, 3 according to the horizontal interval, and it'll be 2, 4, 6, 8 according to the vertical interval. So 3 times 8 is just 24. So the area beneath the velocity versus time graph is your displacement. In this case, your displacement is positive because the area is above the horizontal axis. Okay, so that's important as you will learn how to shade stuff. So therefore, that is very consistent with the math here that I have shown here. So how far did the car go during the first 3 seconds? It has traveled to the right a distance of 24 meters. Okay, so therefore I can just carry my average velocity function down. Delta x here is 24, or you can say positive 24 if you like. Therefore, divided by 3 seconds, So it'll be 24 divided by 3 seconds, which is 8 meters per second. Here I've highlighted the positive sign because it did ask for average velocity. Average velocity is a vector quantity, so therefore you need to include the direction as well. So it'll be plus 8 meters per second, or 8 meters per second east, or 8 meters per second rightward, if you choose to use those terminology instead. Okay, so the answer would be is positive 8 meters per second. The other way to find average velocity when acceleration is constant. So during the first 3 seconds, the acceleration is 0, and it's the same throughout the first 3 seconds, which suggests that you can also use this particular function here to find average velocity. To find average velocity when acceleration is constant, the same constant, you can do VF plus VI divided by 2. Well, what's our VF here? Our VF would be at 3 seconds, but according to the graph, once again, at 3 seconds, if you go all the way up, that'd be a value of 8. At 0 second, you go all the way up, it'd be a value of 8. So it would just be 8 plus 8 divided by 2. Well, 8 plus 8 is 16. 16 divided by 2 is just 8. And here, as you can see, the answer must be the same. So it's important that you utilize this function properly. You can only use this function when acceleration is the same constant. So in this case, the first 3 seconds has an acceleration of 0, which suggests that I can just use it. Okay. Let's go ahead and do part B. Part B asks us to find the instantaneous velocity of v of t at 4.25 seconds. So as you look at this graph here, it's important that you chunk this graph out. During the first 3 seconds, the acceleration is 0. And then from 3 to 6 seconds, I noticed that this is a constant negative slope. So from 3 to 6 seconds, the acceleration is a negative value. And then from 6 to 10 seconds, the acceleration is 0. Because once again, the line here is a horizontal line and there is no slope. So to find the instantaneous velocity at 4.25 seconds, I need to focus my attention on this particular interval from 3 to 4.25. Okay, I want to start at 3 because this is where the car's velocity starts to decrease. It starts to slow down. Why? Because the acceleration here is negative. So the velocity is positive. The slope here is negative, which implies that the acceleration is negative. So if velocity is positive, acceleration is negative, it suggests that the object, or in this case the car, must be slowing down because those two vectors are opposite. So therefore, I can just focus again, like I said earlier, I can start at 3 seconds and go to 4.2 seconds, which is about here. I need to focus on that slope. So if to find final velocity is simply acceleration times time plus the initial velocity. Well, here, I don't know what my acceleration is, but I know my time is 1.25. So if you need to, listen to this again. The reason time is 1.25 is because I'm starting this problem at 3 seconds. At 3 seconds, this is where the velocity starts to change. It was at 8 meters per second, and then it starts to get slower and slower and slower. So eventually at 5 seconds, it came to a stop. So the reason I'm starting at 3 seconds, that is because that is where the car starts to experience a deceleration. So it would be 4.25 minus 3, which is the difference of 1.25. And sometimes kids wants to plug in 4.25 here for time, and that is incorrect, okay? You have to be able to chunk these graphs out, okay? So therefore the time here is just 1.25 because I'm starting at 3, and the question wants me to find the final velocity at 4.25 seconds, which is a difference of 1.25. But if I start at 3 seconds, my initial velocity is 8 meters per second, which puts me right at the beginning of this little purple bracket. Okay, I don't know what A is, but I can find it really quick. To find the acceleration from 3 to 6 seconds, really, because to me, this is just one negative slope. So from 3 to 6 seconds, it's just one negative slope. So you can go from 3 to 5 seconds, you can go from 3 to 6 seconds. You should get the same answer because it's one constant negative slope. So regardless of the value you pick, as long as you go between 3 to 6, you should get the same slope. Okay, so you have to make those choices yourself here. To find average acceleration, you would do VF minus VI over change in time. I'm just going to go ahead and go from 3 to 5 seconds. The reason I'm going from 3 to 5 because at 5 seconds it came to a stop, which makes my final velocity 0, which I think is easier to do. But again, like I said, you can go from 3 to 6 seconds for all I care, and you should get the same negative slope. Try it out if you don't believe me. All right, so final velocity is 0 seconds. The initial velocity here is 8 meters per second. Or how much time? I'm choosing to go from 3 to 5 seconds. Excuse me, watch my cursor. From 3 seconds, it starts at a value of 8 meters per second. And then I want to go from 3 to 4, 4 to 5. That is a difference of 2 seconds. At 5 seconds, the velocity is 0 according to this graph. So therefore, it'd be 0 minus 8 divided by just 2 seconds. So 0 minus 8 is negative 8. Negative 8 divided by 2 is negative 4. So the acceleration here is negative 4 meters per second squared, which makes sense. So if you watch the graph here, that arrow that just came up, that is a length of 8, but it's pointing down because this is a negative slope. So every increment here is 2, so it'd be 2, 4, 6, 8. So 8 down and 2 across, okay? So to find the slope, 8 down, which is negative 8, 2 across, which is positive. So it'd be negative 4 meters per second squared. Rise over run. Slope is rise over run. Your run in this case is negative 8 because it's going down. Your run is positive 2, so negative 8 divided by positive 2 is negative 4 meters per second squared, which is consistent with what we just found here using physics function. So the average acceleration is negative 4 because the slope of this line is a value of negative 4 meters per second squared. So there are different ways to look at it if you like. All right. Therefore, I'm just going to carry my final velocity function down. So final velocity is equal to a times 1.25 seconds plus 8 meters per second. I just found what a is, so therefore vf, wherever a is, I can just plug in negative 4 meters per second square. Time is 1.25 seconds, again, because I'm starting at 3 and I'm going to 4.25 seconds, so the difference there is 1.25 seconds, plus 8 at 3 seconds. My initial velocity is 8 meters per second. So if you simplify that, you should get a value of 3 meters per second. And here I highlight, again, the positive sign because it asks for instantaneous velocity, which is a vector quantity. And because it is a vector, I need to include the direction. So in this case, at 4.25, watch my cursor. Here's 4 seconds, here's 5 seconds. So at 4.25, it's about there. If I go all the way up to the graph, you know, it makes sense, right? If you go all the way, watch my cursor. So 4.25 is about there. So you have to make sure your answer makes sense. If I meet the graph and I go all the way across here, you know, that's about 3 because every interval here is 2. So it'd be 2, 4. So my answer falls between 2 to 4. So positive 3 meters per second is a reasonable answer. In this case, it makes sense. All right, let's go ahead and move on. Part C and D. Part C asks you to find how far is the car away from the initial starting point after 10 seconds. So the first thing you got to recognize is what the heck is going on with this velocity graph. So first, the car was moving at a positive 8 meters per second, which suggests that it's moving to the right. And then it starts to slow down. But as it slows down, it's still moving to the right. And then all of a sudden, from 5 to 6 seconds, it actually turns around. So it stops, and all of a sudden, from 5 seconds, all the velocities now are negative up to 6 seconds. And then at 6 seconds, the velocity is still negative, but now it's moving at a constant rate towards the left. So you have to be able to visualize what's going on with the car here. First it's moving right and it came to a stop and then it turns around, or aka change direction. So let's do part C using visuals here. All right. So the first thing I suggest you do is to draw out a number line. Here my number line starts at 0 because the problem states that the car's starting position is at 0 meters. So it said so. So in my number line, I'm actually going to start at 0. So if it says, you know, if it starts at negative 10, then just start at negative 10. Here it starts at 0, which, like I said earlier, it makes things easy to do. Okay. So in order for you to figure out how far is it from the origin, you have to kind of map out this motion. So chunk it up. Here, the first chunk I'm going to do is the first 3 seconds. Okay. The area beneath a velocity time graph tells you your displacement. And displacement is a vector, so it actually tells you whether you're moving right or left. So you notice here, I only shade from 8 all the way down to 0. This is where your time axis is, okay? So you need to stop. You need to know where to stop. Some kids will shade the wrong area. So t is equal to 0 here, or this is the origin. So you want to shade from where the velocity is just down to 0, and you need to stop there. So therefore, if you find this area correctly, this is 24 meters as we previously found, because area of a rectangle is just base times height. In this case, the base is 3 and the height is 8. So make sure you count your intervals correctly on a graph. And then the next, before I get to the next area, here I have the green arrow. So here it starts at the origin, and because the first 3 seconds, the car has traveled 24 meters to the right, I've drawn this arrow from 0 all the way to positive 24. So this is 24 meters to the right. Okay, but now from 3 to 5 seconds, it's still moving to the right. Well, how do I know that? Because all these velocities are still positive. So if I pick this value here, let's say at 4 seconds, I go across, this is still a positive value. And let's say if I pick, let's say 4.5 seconds, I go across, it is still a positive value, which implies that the car is still moving rightward. It just happens to be decelerating. Okay, so if you find this area correctly, you notice here the area here is above the t-axis. Because it is above the t-axis, the displacement must be positive, aka the car is moving to the right still. But the area of a triangle is just 1/2 times base times height. Here the base is 2 because it goes from 3 to 4 to 5, which is 2. But then the height is actually 8. It would be 2, 4, 6, and 8. Okay, so if you need to, make sure you count the interval correctly. 2, 4, 6, and 8. So you notice here 1/2 times base times height is just 1/2 times 2 times 8. The 2 and the halves will cancel out. It will leave me a positive value of 8. So it's going to move an additional 8 meters to the right. Okay. However, from 5 to 6 seconds though, you notice it came to a stop at 5 seconds. And all of a sudden, after 5 seconds, all of the velocities are negative values. So pick a value here, you go here. It is now beneath 0, which implies that it's negative, which tells you that the object is not moving leftward. And if you pick 6 seconds, all of a sudden at 6 seconds, it is moving at a rate of -4 meters per second, which implies it's now speeding up in the opposite direction. Okay, now we can shade this area. Okay, well, this area here, again, this is just a triangle. So the area of a triangle, which I call area 3 here, because these are 3 different shapes, is just 1/2 times base times height. Well, what's the base? This is from 5 to 6. It's a base of 1. And then as you count down, it's be 2 and 4 because the vertical interval is 2 each line. So 1/2 times 1 is just 1/2. 1/2 times 4 is just 2. And you notice here I highlight the sign here. Because the area is now beneath the t-axis, your displacement is now -2. Well, what does that mean? Well, it tells you that the car stopped at 5 seconds. And then now, according to my green arrow, is now changing direction or turn around. So this arrow here is just -2. So it's going to go from 32 to 30, which is a difference of 2. But we're not done yet. It says after 10 seconds. So this graph shows 10 seconds. So now I have to shade the rest of the area because it wants it for 10 seconds. Well, this area here is just a rectangle. The area of a rectangle is just base times height. Your base here is 4 because it'd be 6 to 7 to 8 to 9 to 10 seconds, which is a difference of 4. But the height is 4 because every increment in the vertical axis is 2. So it'd be 4 times 4, which is 16. But you notice here again, I highlight the negative sign because this yellow area is beneath the 0, or aka the horizontal axis here, as I'm tracing out with my cursor. Alright, so therefore, it is going to turn around and do an additional -16 meters to the left. So this is 30, so to go 16 to the left would put you at 14 because 30 minus 16 is 14. So this is where you would stop for this graph. Okay, but it asks you how far is the car away from the initial starting position. Well, the way you should interpret it is during the first 3 seconds it traveled 24 meters to the right, and then from 3 to 5 seconds it traveled an additional 8 meters to the right. It came to a stop at 5 seconds, but then at 5 seconds to 2 it went leftward 2, and then from 6 to 10 seconds it went leftward an additional 16, which pretty much stops at 14. So therefore the answer would be 14 because you start at the origin and after 10 seconds you're now finishing at positive 14, and that would suggest that the answer is 14. So the length would just be, in this case, 14. It asks for distance, and distance is a scalar, so I would just provide an answer of 14 meters. Okay. All right. Now part D. Part D asks you at which time is the car the greatest distance away from the origin. Using common sense, it would be at 5 seconds. The reason it's at 5 seconds is because from 0 to 5 seconds the car is moving to the right, but then after 5 seconds it turned around. So at 5 seconds it has gone farthest to the right. Okay, because after 5 seconds it starts moving leftward, which would kind of make sense that you're kind of on your way back home. So from 0 to 5 seconds, you are at a distance of 32. So during the first 3 seconds, you went 24 meters to the right. And then from 3 to 5 seconds, you went an additional 8. So really on the number line, the farthest value that you got away from the origin is 32. And when does that occur? It occurs after 5 seconds. Okay, so at 5 seconds, according to the graph, all the arrows are positive, and then after 5 seconds, all the arrows are negative, which suggests you're turning around. So to answer this question, it would just be 5 seconds. All right, let's do part F. Part F asks you to calculate the average velocity during the first 8 seconds, from 0 to 8 seconds. So let's crack this out. It's important that you pay attention to time interval as you practice. So here, I highlighted this from 6 to 8. You notice that's different than previous, because in the previous I highlighted the whole 6 to 10. But part F here only wants from 0 to 8. So I kept the first area the same, which is positive 24 meters. I kept the area for the second triangle the same, because that's positive 8 meters per second, because that's, again, above the t-axis. A3 here hasn't changed. That's still negative 2. But the last segment that I'm highlighting here is from 6 to 8, and I need to stop at 8 because it asks for 0 to 8. So if you find the area of this fourth shaded area from 6 to 8, the base would just be 2. From 6 to 8, the base is 2. And then once again, the vertical increment has not changed, so every line in the vertical axis is by interval of 2, so it'd be 2 and 4. So therefore, the area is negative 8 meters. And it's negative because it's beneath the 0, or aka the t-axis, okay? So therefore, it asks for average velocity, so all we have to do is really map out where does the car stop at 8 seconds. So everything I've kept the same. During the first 3 seconds, the car has traveled 24 meters to the right. And then from 3 to 5 seconds, it traveled an additional 8 meters to the right. But then from 5 to 6, it went leftward, negative 2. And then from 6 to 8, it went leftward, another negative 8. So that puts me at 22. So therefore, in order to find average velocity, I need displacement over time. Displacement is a straight line from start to finish. It says that you start at the origin, but after 8 seconds, you stop at 22, and 22 is to the right of 0. So therefore, we can just apply the physics function to find average velocity. Average velocity here is just delta x over delta t. What's delta x? Delta x is your displacement. So the red arrow here would indicate that you start at 0 and you end at 22, and that is pointing to the right. So therefore, delta x here is 22 meters. And how much time has gone by? Well, the time is from 0 to 8. So therefore, your change in time is just 8 seconds. So if you do 22 meters divided by 8 seconds, you should get a value of 2.75 meters per second. But because it asks for average velocity, I need to tell whoever is assessing you that it is to the right of where it started. So the average velocity is positive 2.75 meters per second. So that is the answer for part F. The one thing I do want to point out that folks often misuse, again, is this function here. Average velocity is equal to VF plus VI divided by 2, which I used at the beginning of the video. The reason it worked for the other part in the beginning of the video is because it only asked for the average velocity from 0 to 3. Well, from 0 to 3, the acceleration is 0. However, for this one, it went from 0 to 8 seconds. So it's important that you recognize the acceleration from 0 to 3 was 0, and then the acceleration from 3 to 6 seconds was negative 4, which suggests that the acceleration is no longer the same. The acceleration for 0, and then it went to negative 4, and then from 6 to 8 seconds, the acceleration went back to 0. So the acceleration has changed during this 8-second interval, which implied that you cannot use this function. You can only use this function when acceleration is the same constant, like it has to be the same number during the interval that you're using. For this one, from 0 to 8, the acceleration from 0 to negative 4 back to 0, which implied that it has changed. So therefore, you cannot use this average velocity function. So it's important that you apply physics functions correctly as you practice, okay? Let's do part G. Part G asks you to find the average speed for the entire 10 seconds. Well, this one's pretty whack. I already know a lot of the answers here. So therefore, I'm just going to go ahead and crack this out. Average speed is distance over time, but distance is just a scalar. It has no direction. So therefore, I know that it went 24 to the right, 8 to the right, 2 to the left, 16 to the left. However, distance, you just add everything because distance is scalar, so you just add 22 plus 8. Why I highlight the negative sign here for -2, that is your displacement. But distance, we don't really care for the direction. We just count every single step that you take. So it'd be 22 plus 8 plus another 2. And then why this is -16, we're just going to add 16 steps because it's distance. Add another 16 divided by 10 seconds because from 0 to 10 is 10 seconds. So if you do all that, you should get 48 meters divided by 10 seconds. So the answer is going to be 4.8 meters per second. Okay, so differentiate between average velocity and average speed. Know when to use the displacement, aka the vector. Know when to just do the absolute value and ignore the negative sign. All right, I hope that helps. Stay nerdy. Don't be whack.